Allow me to continue where I left off yesterday, which was essentially introductory remarks. You will notice that equipment continue to dissipate heat, and I have also told you about saying there is always what do you call a loss for the intended function. The simplest thing we can talk about is probably a power supply, which the input is 230 volts and then the output is typically if you take a computer it is around 18, 19, 16 and a half and all that. So, for a nice rounded thing, no, let me take the output is 20 volts and the input is 230 volts. And then there is an input current, and if you multiply the input current and the input voltage, and then because of the nature of the switching regulator a power factor, we get a wattage, which is typically the heating value of the thing. So, even if you have seen good old RMS power calculations, RMS is still mathematical. The actual thing that is accepted is what you call heating value. So, if you have a resistance or if you have anything, you know very well, irrespective of the what do you call the voltage and current waveforms and the phase difference between them, what finally matters is the heating, which is the power, actual power consumption, power conversion. Now, all electronic circuits they try to be as efficient as possible, but the reality is there is a range of load conditions in which it is optimum, design is optimum. Anything less load it does not work, anything a higher load it becomes inefficient. So, inefficiency of electronic circuits invariably ends up as heat loss, and heat loss is real. So, you would have seen it in the case of anything which you come across in at home, and the magic is, the idea is how to predict the heat loss. So, it is not as if I am the only genius here who has come and think. See, if you go to the internet and just give a casual search on convection or heat and mass transfer or heat sink calculations, you have multiple hits, and in fact at the top, yesterday I was telling you it's lot of hits. Seen this 3000 results on YouTube, and all related to only heat and how to deal with how to manage the heat, and secondly a lot of them are public lectures. Now again there also, as I said, allow me to point out, we clearly have two types. One is where the teacher wants children to, not children, I say knowledge seekers to understand. So, if you see here we have a lecture on heat transfer by, I suggest you do it, and then similarly heat exchangers, heat transfer, and then convective heat transfer, and so on and so on. So, one part of it is by lecturers and teachers who want all the knowledge seekers to understand how the final formula has been derived. It is possible for us to use it in conditions if the main problem has been broken up into smaller things, and then when you have a complicated, you have seen this, all of that fundamental analysis has eventually ended up in software, or I will say, I will use the word code. Somebody has coded all this and have presented a very beautiful animated image. I am not sure whether this is really simple straightforward animation or it is an analysis from a package which uses both FEA and CFD, and then gives you these nice pleasant results. One thing you would have noticed is in a generic case it is very useful. In a very generic case, meaning you know the spin spacing, you know the profile of the fins, and then you know various things about fin effectiveness, and then the heat transfer coefficients. But in your individual case, these things may or may not really make any sense. As I said, if you remember, I tried to show you this phone. This has 5 to 6 radios. Some of them are on simultaneously, some are not. And then you also have a charger, a power charger. Usually because of the layout it is kept close to the 5 volts input. So, somewhere here there is a power charger, then there is thing, and lot of them are being built these days with wireless charging. So, you also have a wireless receiver, and all of them are unique. Every instance is unique to the, it is not easy for us to say sin. Again, one more thing. Now, one very interesting thing you will notice here is, this is typical of the Peltier module I had shown you yesterday. Do you remember that? So, it is conventional and maybe a little to do with our definition of what you call red and blue and all that. No, left side is a pin fin heat sink, which is trying to what do you call extract heat from the, I think the one surface of the Peltier whatever module, and then you see it is kept red, saying it is hot. On the other side, the blue shows that same thing. No, again heat is being exchanged to another medium. Blue is typically cold, something to do with infrared being hot, and then our the other end of the spectrum not being contributing to that. So, it is conventional that it is, but it is not as a blue light automatically cools or infrared heats or anything. Infrared heating is real, the other part you have to see in due course. So, if you see things like this are possible, and if you have the Peltier junction in between, and then we can always extract heat from one surface, and then you can transfer it to the other surface. Again, by convention here, I expect that one of them is a hot surface, and then I will avoid the judgment saying which side is hot and which side is cooled. I think you should figure it out yourself. Now, I will come to the more things. These are all taken from, they are not mine. We come to the second type of how do you say data which is available on the internet. The second type of data relates to manufacturers who have actually attempt to fabricate devices which are useful for us. That is in this case that is a cooler. Loosely the word Pentium cooler is used, but I expect it is any cooler which is built into most of the we call our common ubiquitous personal computers. You see, at the base of it we have a, at the base somewhere mounted on the circuit board is probably the what do you call the source of heat. In this case it could be any chip, and then you see here very elaborate arrangement has been made to hold the chip, and then you have a heat sink here, and then on top of it you have the small fan which sends what do you call air onto that. If you remember what I was trying to tell you yesterday, you will notice that the profile has been made somewhat carefully this so called heat sink profile, you see at the base, it is thicker in the middle and it slowly tapers off into the corner. This is where a little by what you call actually making and finding out, and a lot more these days by analysis they have found out how to maintain the fin effectiveness. In this case, again coming back to the old this thing, the vertical fins are spaced evenly and they are thin. So, it will be appearing to slightly violate what I have told you earlier. In the case of forced convection, we expect the fin tip to be thin, and then all along the fin the temperature is they try to maintain it high by making it little thicker at the base, but then it will interfere again with the flow of heat, smooth flow of heat. Somewhere they have made a compromise. Probably they have taken the same raw material, and then they have probably cut fins, actually mounted it with different fans, found out one particular combination which seems to work well. So, this optimization keeps doing well. These industry standards people also know, they keep trying it and all sorts of things. The very fact that heat sink catalogs are big, thick, and there are so many of them shows that they are still under development. For every unique case, you need a different heat sink. A reasonable example I can tell you is, we have come to this LED lighting, and commonly we think LED lighting is all about replacing a bulb. So, the word LED bulb also is used. Now, most of them are a chip LED, and at the back they get hot. So, how does one now cool these devices? How do you do it? So, you have a chance for a new heat sink. I hope you got my point. My point is that any time a new application is found, typically the so called LED bulb, there is always a chance of having to make a new heat sink. So, multiple attempts are made. One way the attempt is made such that the heat is minimized, and in that case the load is practically constant. If somehow you regulate the input voltage, and then if you maintain the current, we can make a proper switching device which will keep the heat low. And then LEDs are being improved such that a LED typically which gives about 250-300 milliwatts does not need a separate heat sink. If you can just put it directly on the copper lead itself can be made to carry certain amount of heat. So, somebody is working on these things all along. You need to just see the next picture. Again, it is taken from the internet. I am not sure whether it is experimental, it is real, or what is it, but you will notice here now it is again somebody is trying something. They have tried to stack copper plates. I am not very clear whether it is experimental or what is it. And what I call, there are overclocking enthusiasts. They seem to play with water cooling and so on and so on. You see here there is a stacked plate of something underneath, I am not very sure. So, these things seem to be working all the time. So, you have a circular heat sink with radial fins. They are not just radial, they are strictly not radial. If you see they have all been made sort of halfway between tangential and radial, because when the air from the fan spins, it seems to also take it into a particular thing. So, it makes sense to make things like that. And you see at the core of it, simulation has yielded a beautiful red color. So, obviously that red color is where it continues to still get hot, and the tip is cold, relatively it is cold. So, this is where the heat sink manufacturers try to make something. Next time when you get a chance, when you have so many of your what do you call e-waste. So, if you have an earlier series of computer, there are two ways of it. One of it is the outside box you can remove and then use it as a footrest, and the inside lot of hardware is there. One of them typically is the cooler which is there. Next time I suggest you open the cooler, have a look at it, heat sink, turn it upside down, you will notice that the core, while the outside is an aluminum, the core is made with FRHC copper, fire refined high conductivity special copper, and then they make a copper slug, and the copper slug is attached to that. That is the only known material, and probably they have modified it with the proper appropriate metallurgy to have the lowest conduction. You understood, no? I am sorry, highest conduction and the lowest what they call thermal resistance and conduction. Now, when it comes here, this it makes things easier. See here, while that thing is swirling, this thing seems to be directly being taken out radially, because this is a pin fin heat sink, same circular pin fin heat sink. In the case of a pin fin, all the things are going up. Now, this is where what you call our creativity comes. One is try to use strictly a trial and error hit and miss method. Another is try to use a little bit of your analytical tools and then try to design. So, the what you call manufacturers all the time seem to be making these things. I do not know if it is visible, but maybe if you enlarge it, you can definitely see it, and then depending on your, you have seen something very, very interesting about here. The material conductivity, obviously silver is the best conductor. So, it is pure, and other than making a what you call small black coating on it when exposed to the atmosphere, it thermal conductivity watts per meter per degree centigrade, it is all the highest is thing. Next, as we all know right from what do you call our old physics, I do not know whether you study it when you are about 11 years old to about 15 years old, you would have been taught that gold is not such a good conductor of heat. We do not know how it has happened. Next best is copper, but we see that if you go for copper, first of all copper has certain disadvantages. One of them being it is not that easily available, and we have, unless it is a very critical application, they do not use it. So, next best obviously is aluminum. So, right now a combination of copper and aluminum, well you have a core which is made of copper, and then you have aluminum which is used in the fins and all that, which can be worked upon, seems to be the choice which people use. However, if you remember my last what do you call lecture, I have shown you most equipment, the enclosure material is probably steel, loosely we call sheet metal. So, coming back to my this thing here, and then that has a small element of usually carbon, which makes it what you call mild compared to hard steel. So, you see carbon steel or the usual mild steel, still compared to aluminum and copper, it is very, very low. And then insulation is real. Follow insulation, that is whenever you want to have any active device, and especially if it is one of the what do you call connections is attached to the case, as in the case of a power transistor or a switching transistor, and things like the old TO3 and now we have this 220. We need to isolate the that what they call mounting device. usually it is the collector or the emitter. So, depending on PN, no, one of them, that small aluminum thing is needs to be insulated. The first insulation we can think of it is probably, you see here, the simplest insulation we think about is PVC, PTFE or paper, but all of them now seem to be not so great. Thermal conductivity is not good. So, work is going on about trying to make silicone pads, that is again a proprietary item by which they have a matrix, a fibrous material which is impregnated with silicone materials, and the whole thing is cured, and then it is available to you in sheets. Those things have very good electrical insulation properties and very what do you call good thermal conductivity problems, which is slightly different in nature. So, we will come to this sort of lot of figures. You see here, this is a pin fin heat sink, and then you have noticed something which is we will slowly getting it. It is saying, other than the basic thermal aspects, we also end up with this sort of mounting. You have two mounting tabs that are given here. So, it occupies space. Is there a better way of doing it? And then do you just need to put force, or underneath that do you put some thermal what do you call paste and leave it at that, or use the paste itself as a bonding material? Can you make a thermally conductive setting adhesive? So, you have these epoxies which are also thermally conducting, plus they set. So, the forces are a little low, and then you can avoid the tabs which are present there. Yeah, I think this if you remember, I was trying to show you this yesterday. This is taken from some game console. So, you have seen this, there is a hood on top of it, and then that hood has been removed, and then at this back, no, actually it is turned around. There is a fan here, and then the fan seems to blow the heat inside. The next pictures will show you a little more about this. Notice something as is before, sorry for repeating it. They are thin fins, and then they also appear to be tapered from the bottom to the top. They are a little tapered, and then the place here for the fan is not directly attached to this, and what do you call, there is a cowling which was attached. In the previous picture I showed you the cowling, and the air is blowing that side. This is the same view from the other side. Why did they make that all that, what do you call, why did they go to great lengths to, if you see this profile, have you seen, this seems to be a normal extruded heat sink, and then after the extrusion is done and everything else is done, they have gone about making machining such that these screws sit here, and then there are, I am not very sure why these openings are there, but one thing you notice is it has been machined in a peculiarly, what do you call, a geometric ordered way. This is the reality of products and design for products. Well, in the case of analytical things, we take an aluminum block because it is easier for us to test, and then especially if you have multiple choice questions, tick one of them. There we talk about saying take an aluminum blocker and then imagine there are rows of what do you call slits in it, and we analyze it. But in reality, if you see none of that length of where the total area is available for you to do the convective heat transfer is not constant, it seems to vary. In this case, luckily it is a geometry, it is slightly easier to model. But the actual reason why they are forced to make it and make a very complicated heat sink like this is dependent on the actual packaging issues. So, you cannot treat anything in isolation. If you see here now, can you see? You have a fan there and then you have a cowling and it comes here and then it blows here. This clearance is required for the air to be drawn in. You understand? No, all the accumulates, air accumulates and then comes through those spaces in between and comes out. So, based on physical layout, based on other considerations, these non-electrical items including what you call the mounting screws, including various things are there. And then I have told you about, I think in another picture now I have told you how various antennas and all are made, maybe that is one of the antennas. So, you have this tremendous amount of influence of physical layout of the equipment on design of the other things. So, you need to pack them where all you can. You have seen this is what I was trying to tell you. Now, I will try to go up again. I do not even know what it is. You will be surprised if you take a device like a like this. It gets hot. So, if you see the specs on the charger, typically the charger specs say 5 volts and about 2 amps, but 2 amps may be peak, it may not be what you call continuous. And then secondly, when they talk about an intelligent charger, I do not know how, whether the charger sees the load or the load communicates with the charger. Some tricks they employ, maybe signals are sent via the PWM thing and all that. Now, you see if I take a thing like a 5 volts 2 amps per hour supply, we are pumping 10 watts and I do not know how much of it is actually goes into this battery. Some of them are a single cell 3.7 volts, some of them are a collection, they are parallel, and as if life was not complicated enough, we also have wireless devices. Some of them have 2, 3, 4, 5, 6 wirelesses in that. We are all familiar with good old GPRS. And then as the new LTE and all have come, some of them it look like they end up with 2 antennas. One antenna is used for transmit receive, one antenna is for receive only. And then same thing with Wi-Fi. Sometimes they say Wi-Fi also has 2 antennas. As if our life was not bad enough, we have a NFC communication, very near field communication. And then we have Bluetooth. And then after everything is over, suddenly wireless charger has come into place. So, everything requires access, everything has some inductive elements, everything needs access to the surface, plus that same surface is required for us for cooling, and several of them are probably made of special plastics. So, you see this is typically in one of those, as you said, very common thing, which I just picked it up from the internet. Hey, very tough for us, no? Now, how do you cool a device like this? So, in this case, Inside the enclosure we have cooling only, and somehow all the stuff is brought to the surface, and hence occasionally you will find it surface being hot, and then electronics has been made such that it minimizes everything. Only during charging you try to what do you call give continuous power, and in the case of use, even when the device is communicating with the tower, it will only communicate in short bursts, which shows that I am here, but with every burst we have energy being radiated. All the energy that is not being radiated ends up as heating of the chip. So, and for the purposes of assembly and disassembly, even these connections and all have been made into a zigzag pattern, so that an accordion type construction is given, so that it will come out here. This is typically, then maybe I should stop here and go back to the starting point. So, even if you see in the case of something which is mounted on